Welcome to Study Loop.
In state 1, the refrigerant is a saturated mixture. The same in state 4 and state 3. In state 2, the refrigerant is a saturated vapor. So in all four states, we can use the table of saturation properties to find the temperature of the refrigerant at the corresponding pressures. So the temperature of the refrigerant based on that table at 90 psi is 72.78 degrees Fahrenheit. At 30 psi it's 15.37 degrees Fahrenheit. Let's first find the coefficient of performance of the refrigerator. This is formula 11-7. TH is the temperature of the heatsink. TL is the temperature of the low temperature source. Please note that both TH and TL are expressed in kelvins, not in degrees Fahrenheit. So you'll have to convert these values into kelvins. The answer is approximately 8.27. In order to solve part B, let's first calculate the specific entropy of the refrigerant in state 3. So you can find this formula in the book. It expresses the specific entropy of a saturated mixture in terms of the specific entropy of fluid at the same pressure. The difference between the specific entropies of fluid and gas and the quality of the mixture. The specific entropy at state 4 is the same as at state 3, but on the other hand, one could use the same formula to express the specific entropy at state 4 in terms of the specific entropy of fluid and the difference between the specific entropies of fluid and gas at the same pressure and the quality of the mixture. In this way, we express the specific entropy of the refrigerant in state 4 in terms of the quality of the mixture in state 4. And this is the quality of the mixture is the quantity that we are looking for. So we can now isolate this quantity, but S4 equals S3, so we can substitute S3 in place of S4. So we can substitute this expression into this expression in place of S4. And then X4 is going to be expressed in terms of the known quantities. The answer is approximately 0.237. Now to solve part C, let's find the amount of heat rejected by the heatsink per 1 kg of the refrigerant. It equals the difference between the specific enthalpies of the refrigerant in states 2 and 3. So the first one is easy to find because at state 2 the refrigerant is a saturated gas, so we can just take this value directly from the table. In state 3 the refrigerant is a saturated mixture, so in order to find the enthalpy, the specific enthalpy of that mixture, we can use the same approach as in part B. Let's remember that from the conservation of energy, the amount of work performed by the compressor plus the amount of heat absorbed from the low temperature source equals the amount of heat rejected by the heatsink. Also, from the definition of the coefficient of performance of a refrigerator, the coefficient of performance of a refrigerator equals the amount of heat absorbed from the low temperature source divided by the work performed by the compressor. So we can multiply both sides by W in and then you get this equation. We can now substitute QL, this expression for QL, into the first equation and then isolate W in from the resulting equation. And now W in is expressed in terms of the known quantities because we already know QH, we have just found QH.